Hey everyone, welcome back to my daily coding series. Today is day 52. So I'm going to do something similar to yesterday and just go through some easy problems today, and then probably tomorrow I'll get back on the LeetCode 150. It looks like I never solved this one. So let's try this one. Longest common prefix. All right. Write a function to find the longest common prefix string amongst an array of strings. So all right. So sorry about the whistle. So I'm thinking, so we can just go from I equals 0 until I equals the minimum length and just check if I equals the character in every word. So there could be 200 strings. So we'd have to check like, does it equal, all right, so we'll say I equals 0 while I is less than, for now I guess I could say just M is equal to, or L is equal to the length of the minimum of strings. That might not work. I could also use try and except, or I could just make my own function. Well, okay, so I'll just write the trivial way of doing it. So I guess you could just say while true. So basically you just keep going until, yeah, so I guess we can say while, so we want to just compare the first, all right, I'm going to treat this like a technical interview. So let me, instead of trying to solve it as fast as possible, I'm going to just walk through my thought process. So let's just, let's restart. Okay. So our goal is to write a function to find the longest common prefix. So if we have, how many words do we have? So we can have up to 200 and each could be 200. Okay, so if we look at the first example, we have flower, flow, and flight. So we're going to have a pointer. So we'll say like I equals 0. And then we're going to check for every word if they all equal the same thing. So we'll have I all equal here. Okay, I all equals F. So then we'll have a result list where we put F, and then we move our pointer up. So now I is 1. And now we check, is I bounded for all of them? And does it equal the same character? So yes, it does. And then when we get to O, we see that it does not equal the same, so we just exit out. Okay, so to get the minimum length would be O of n. So we could go till a minimum length, or we could just keep looping and then check every time. I don't like using while true normally. I guess what I could say is, so we'll set I equal to 0, and then our condition be, and then result will be empty, and then while they're all equal. So, okay, I'll just say while true for now. So while it's true, for word in strings, so we'll say like all, yeah, we'll just do nothing. Okay, and then if word of I does not equal so I'm thinking we can just store, so how would I do this? I would want to check word of I, make sure it's equal there, make sure it's equal here. So would we have like another loop? So we could say j equals 1 while strings of I of j so the character will be strings of I of 0. So that'll be like this f. And now I want to check, are all of these f? So this will be j. And we'll say while I of j, so does I ever increase? All right, let me just do min length equals the minimum of length word for word. So we can just do that, and then I'll say, well, I is less than min length. I was trying to avoid doing this, but I think it's fine. And then we'll have I go up by 1. And then j, well, here could we just say, so yeah, so the inner for loop. So we have an I pointer, right? So we'll say I equals here, and then we'll set j. So we basically want it to be like j, and then j, and then j, and then we'll have I go here, and then j, j, etc. So that would be the length of strings times the length of each string. So that could be 200 times 200. Okay. So that's 10 to the 2 times 10 to the 2, which is 10 to the 4. So that's like 10,000-ish. So 40,000, I believe. Times 2 would be 400. Yeah, so 40,000, which is fine. So n squared should be okay. And if you think about it, just like one giant string, I wonder if there's like a more clever way to do this with list comprehension. But maybe not. It might be good also to just make a different function for clarity. So what if I have a function called like same at I, or same character, which takes an I. And then it would also have, of course, strings, so we would just return for word in strings, we want to say if, yeah, so then we'd say char equals word of I, and then if word of I does not equal character, then return false, otherwise return true. So this would be a little function. So we take the first word, and then we see for every subsequent word, so for every subsequent word at position I, if it doesn't equal, then we'll just return false, otherwise we'll return true. So what we want to do here now is, did I mute? No, okay. So what we want to do here is set I to 0. So we're going to just loop through them. And now we will call the function. So if same character at I, then result dot append well, we want the actual character itself, right? Well, I is less than min-length. So how would we get that? I guess we would need, and word doesn't even exist really. So could we return maybe a character? So we could return, but word doesn't exist. So instead of word of I, would we say strings of 0 of I? Yeah, that makes sense. And then of course it would do one redundant comparison. So if it doesn't equal char, maybe we could return like -1. Or just, can we return a Boolean and a character? That would be interesting. So if, I actually don't know if you can have a function that returns different. I don't know. Let's try it. I don't know. I feel like that's bad design. Yeah. Okay, so if position 0 is the same character. Oh, I have an idea. Then you can just append, all of it's the same, so you can just say strings of 0 of I. And otherwise, if it's not, then, I'm on my Spanish keyboard. Yeah. Wait. Okay. Otherwise, if it's not, then you just return return the joined result. Okay, let me try this. Okay, I feel like that took me way too long. I think a problem that I have is I constantly am trying to optimize throughout the problem because I think I have a thought in my head like, oh, this is an easy problem, so I have to do it really well. So I'm uncomfortable with doing sort of not the most optimal solution right away, but that is the best way to problem solve, is to do not the best solution right away and then kind of narrow it down from there. So in essence, I should be more comfortable doing less optimal solutions for easy problems, or problems that not easy, but problems that I like, quicker problems, I guess. Okay, so that's that one. So let's go back here. So this should be done now. Okay, so let's try square root of x. All right, given a non-negative integer x, return the square root of x rounded down to the nearest integer. The returned integer should be non-negative as well. You must not use any built-in exponent, function, or operator. Okay, so initially what I'm thinking is we can just do like a linear, so for 4, for instance, but I can't use exponent operator. Can I use multiplication? So I could say, so if our target is 4, I could check all numbers from 1 to 4 and say, hey, does 1 times itself equal 4? If not, then I can keep going. Does 2 times itself equal 4? Yes. The problem for this is when we get to something like the square root of 8, we would say, does 2 times 2 equal 8? No. Does 3 times 3 equal 8? No. So we know that it's in between 2 and 3. And then could we... so if it's in between 2 and 3, then we take 2. Right? So it's... I wonder if you could use binary search on this problem, actually. That would be interesting. I could try that. But I think so going back to my point that I said after solving the last problem, so what I'm going to try to do, I'm going to say for I in range, length of x. So we're going to go from 1 to x. And we're going to check, does I times I equal x? If it does, then, all right, so I'll just do it like this. So does I times I equal x? Then we, of course, will return I. We found the square root. Otherwise, if I times I is greater than x, so like in this case, 3 times 3 equals 9, we want to return I minus 1. Otherwise, keep going. So if it's less than, so for instance, 2 times 2 is 4. 4 is less than 8. So we should just keep going on to 3. So let me try this. Int has no length. So we just want to go from 1 to x. Okay, let's submit that. Wrong answer. So with 0, I guess I should have looked at the constraints here. So if we start from 0, then 0 times 0 will equal 0, and then we'll return 0. Oh, it's because our target number is x. So if you go in range 0, your program will not execute. So I can just say, as a base case, or as a edge case, if x equals 0, return 0. And then I think that's the only edge case we'd have to worry about, because 1 will... okay. I thought for sure if x equals 1, so let's see what's going on. So it'll say if 1 times 1 equals 1, return 1. But it appears I'm returning nothing. So our input is just 1, and I'm saying, oh, should we say x plus 1? Is that what it was wrong? That would make more sense, actually, because now that I think about it. So 0 and 1, the square roots are itself. Okay, perfect. So I'm very slow on this. So I'm guessing that a binary search is much faster. So here's the linear solution. The way I would binary search this is I would say, so L is going to be 0 and R is going to be the number. So X, because there is no number which its square root is bigger than itself, with the constraint that the number must be a non-negative integer. So we're going to binary search it. So we'll say that while L is less than or equal to R, if, and then we're going to calculate M. So M will be equal to R plus L, integer division 2. If M, so here's how we're going to check it. So if M times M equals X, then we'll return M. Otherwise, if M times M is greater than X, so if it's greater than, we want to set R equal to M minus 1. Otherwise, if it's less than, we want to set L equal to M plus 1, like this. Okay, so then when we're done, so imagine we have, let me just, I think an easier way to do it would probably be print L and R. I think it'll be one of those. Yeah, R would make sense because we're rounding. I don't know. I think I just have a feeling that it's R. Okay, there we go. So, looks good. Even though it says 28, it's probably pretty close to... Yeah, it looks like binary search is the way to go. Okay, so you can... Here, because the information is sorted and you can get information about which direction you need to go at every step, then you can use binary search. All right, next up is remove duplicates from sorted list. All right, it's a linked list. Given the head of a sorted linked list, delete all duplicate elements such that each element appears only once. Return the linked list sorted as well. Okay, so I think what we're going to do is if we have a linked list, for instance, if we have 1, 1, 2, 3, 3 like this, we are going to set L and then while and R, and then while R equals L, we're going to keep going up by 1. R equals L, keep going up by 1. It no longer does. So what we're going to do is set L.next equal to R. So this will get deleted. L.next equal to R. And then we'll set L to R. And then if they're not equal, then you just, I guess, yeah. So I think what you do is you set L to be here. So we say L equals head and R equals head dot next. And then we say while L dot val equals R dot val, R equals R dot next. So we'll keep increasing R until it eventually doesn't anymore. And when it doesn't, we will say L dot next equals R. And then we can say L equals R. Okay, and we want to keep doing this until, so while R is not none. Okay. And then what we want to do, okay, so let's assume that we already have a sorted list with no duplicates. Okay, what's the behavior that we want in the normal case? So L and R will start here. So what do we want? We want R to move 1 and L to move 1. So in other words, if it is a duplicate, so we always want, so maybe instead of doing this, so we both want them to move. So it should be L equals L dot next and R equals R dot next. But, so we want them to move every time. And then if they're the same, so if we have 1, 1, 2, 2, and we have L and R, we just want R to move and L will stay the same. I could say like temp equals L. And then here I could just say L equals temp. So like we'll move them. So what I'm thinking is we'll move both of them. Maybe we should move them afterwards. Or we could say while temp.val equals. So like this. So we'll store these in temp as L. And then, so again, I'm not going to try to optimize too soon. And then here we'll say temp r.val. Okay, so we'll store these. We'll move them up. If they're the same, then L will go back to where it was. So 1, 1, 1, 1, 2. So we'll move both of them. They were the same, so L goes back. So maybe this should be an if statement. Okay, so then we store them again, move them again. They were the same, so L goes back. This doesn't really seem right because, again, we need to, so we have the pointers correct, but once R, L, so L will go back, and then we can check, like, if L doesn't equal R, so if L dot val, then we can say L dot next equals R, and then after that, we want L to go to temp R. Okay, I'm not sure if this will work. It might have too many steps in it. None type has no attribute val. Let's see if that does anything. Do I not return anything? I should return. Do I just return head? Okay, I'm not really in love with this code. Let me slow down again. All right, so if we have 1, 1, 2, I think I have the right idea. I'm just not doing it the right way. So we should have L and R. While R, all right, let's just write the inside of the loop first. Okay, while r.val equals r.val, we want R to equal r.next, right? So we want R to go here, R to go here, and then when it's no longer equal, so when we break this, it has to not be equal. L.val does not equal. But there is a case where it could be none. So let's imagine it's not none for now. So R could also be none. So let's assume that it's not none right now. So ideally what we want to do is position L to be R and then to continue. So we can say L equals R. Sorry, L dot next equals R. So this part will get rid of the, so we're basically going to move, so L dot next should be R, so that will delete this, and that'll be that. And then we want to move L to R, so we could say L equals R. And then we want to continue this loop. So we want to do this loop until while R. So what we could check here is if not R, so if it's null, then we'll say L dot next. It should point to just none. Okay, so that looks good. So, and then maybe we can say, so that handles that case. So for instance, this should work for the first test case. So let me just verify that. Yeah, so if it's null, then we can do it here actually instead. So this should work for the first test case like I was saying. Okay, it worked for this one as well because there's duplicates. In the case that there is no, so it should fail when there is, okay, so it didn't fail, so let me understand why. I thought it would fail in the case if you have, for instance, this, right? So for instance, I thought it would fail here. So if you had L, R, they're not the same, so this wouldn't even happen. And then you'd say L dot next equals R, which is what? So wouldn't you set, isn't that setting it to itself? Oh, no. Okay, so this actually would trigger one time and R would equal R dot next, like that. And then you would set the next, and then you would say L equals R. And then they do equal, so then you'd move it. So it does kind of traverse. It feels kind of hacky, like I wonder if it would be more readable if I had an if statement. That checks like if they're not the same, then just increment. But it's kind of weird the way I'm doing it because it will always be the because I'm setting L and R to be the same thing. It'll always be the same, so it'll always move R. So it just like happens to work identically with the case where they are the same. But yeah, I'll take it. All right, next one. So we've done 3. We also did number 14. So we did them in that order. Okay, so next up is, so we just did remove duplicates. So now let's try merge sorted array. Is this just the merge function? Okay, so I have this one. Oh, don't return anything. Modified nums1 in place. All right, let me read the instructions. So you're given two integer arrays, num1 and nums2. So 2 lists of integers sorted in increasing order and 2 integers m and n, which are the lengths. Merge nums1 and nums2 into a single array in sorted order. The final sorted array should not be returned by the function, but instead be stored inside. Stored and sorted are anagrams inside the array nums1. To accommodate this, nums1 has a length of m plus n, where the first m elements denote the length that should be merged and n elements are set to 0 and should be ignored. Okay. So we're basically going to have to merge. All right, because usually I do this, the merge function, like for instance in merge sort, but here you do it in place. So I don't know if that's how it's actually implemented, but let's see what we can think of here. So we have 1, 2, 3, 0, 0, 0. And for n, or for nums2, we have 2, 5, and 6. So the standard approach to this problem is you have 2 pointers, I and j. And then if I Okay, so if I is less than j, in this case, if I is less than j, we increment I by 1. That's normal. and we'll say if it's less than or equal to. So then we'll increment I again. In this case now, j, all right, so let me write that down. So if I is less than or equal to j, just I plus plus. Okay. Now, in this case, I think we can do something interesting, which is we swap these two numbers. So 2 goes here, and then we have 0, 0, 0. And then we put 3, 5, 6 like this. So we swap these two numbers, and I goes up. Now, does it have to be 0, or can it be negative as well? So I guess when I equals, so maybe we can do that. So if otherwise, swap I and j, so like a of I and a of j, I guess it would be m of I and n of j and I plus plus. And then we can, whenever I equals the length of n, so stop when I equals length of m minus length of n. So in this case, 6 minus 3. So when we have 3 spots left, then we want to stop. If we had another one here, we'd want to stop at 7 minus 3. Yeah, okay, so I think that's right. So let's try it. So we'll set I and j equal to 0. And then we'll say while I is less than the length of m minus the length of n. So I always goes up by 1. And then we'll say if j is greater than I, then we'll swap them. So we'll say temp equals m of I. Then we'll say m of I equals n of j. And then n of j equals temp. So we'll swap them. And then once we get to this point, we know we can just fill in the rest. So we'll say while I is less than the length of m, we will say that m of I equals n of j. And then also j will go up by 1. Sorry, j will go up by 1. All right, let's see where this gets us. So this would be my initial attempt at this, and then we'll return, what do we return, n? Okay, so instead of m and j, I want nums1, which is m and n, and then I wanted nums1 for m, and nums2 for n. Length of m is just m. This is nums1, and this is nums2, and then we want to return nums1. All right, let's try that. All right, wrong answer. So let's look at it here. So what did I return? 256000. Did I reset I? All right, so let's see if the algorithm that I thought of works. So we have 1, 2, 3, and 2, 5, 6. Yeah, so 1, 2, 3. So I'm guessing it's an implementation error. So at this point, let me print what I is. So it should be, so my standard out is 0. It's less than m minus n. The length, I think I want to say, well, so what is m minus n? So it looks like that loop is never executing at all. M minus n is 0. Oh, okay. I thought this was length m, but it's just giving me this. So it's the same as m plus n minus n, which is the same as m. Okay. So now it's telling me 3, 0, 1, 2, 3. So at this point, let me print nums1 and nums2, so that way I can see what's going on. Okay, so nums1 is this and nums1 is 2, so it didn't do anything. Oh, I'm looking at j. Oh, okay, that's why. So it should be if nums2 of j is greater than nums1 of j. So I should have been checking the values instead of checking the index. So it's out of range. So let me print ij. So j is never going up. So I has to be out of bounds. So let's see. Test result 0, 0. Was it just for this one? All right. Let me just do this edge case. So if not nums2, return nums1. All right. So no index error. So it's printing 2, 2, 3. So why did we swap 1? If nums2 of j is greater than, did I mean to say less than? If this is greater than, then we want to swap. So print swapped. Yeah, I think I'm definitely on the right track. It's just a matter of debugging at this point. Okay, so we swapped. So so we should not be swapping. So nums2 of j I think this sign is incorrect. I think the sign was incorrect. Okay, looks good. So it's 1, 2, 2, and now because I is equal to 3, this should go to m plus n. So yeah, initially when I coded this, I thought that I thought m was 6, but it was not. All right, so let's submit that. Wrong answer. Well, no, we do want to swap. If nums of j is less than it, then we do want to swap. So 4 swaps with 5. And then I goes up by 1. So I is now 6. And now 5 swaps with... Wait, but this isn't sorted. Is nums of 2, it's not a requirement for nums of 2 to be sorted? Maybe I missed something. Okay. Oh no, it was sorted. Okay, so maybe after we swap, we need to do, that's weird. Because normally after you swap, J goes up. Is it just merging? I think it's just merging and I overcomplicated it and I was confused about M and N. Because normally what it is if you have two, I think I just, the in place thing kind of confused me a bit. So what is it? If we have 1, 5, 6, and 4, 2, 3, then we have I and J. Yeah, the in place thing is a little confusing. So normally what you do is say, okay, 1 is smaller, so we'll add it to our list. And I goes up, okay, 4 is smaller, so we'll add 4 to our list. Wait, this shouldn't be 4 though. All right, it's 4, 5, 6, 1, 2, 3. Okay, so we have I and J. So J is smaller, so we're gonna add it and then move up J. J is smaller again, so we're gonna add it, move up J. J is smaller again, so we'll add it, move up J. J is out of bounds, so we add the rest of this. So I could totally do it like that. That's just the standard merge function. But my question is, how do I do it in place? Whoops. How do I do it in place? And now I exited out the test cases by accident. It's a disaster. So how would I do this? So we have 4, 5, 0, 0, 0. So I think I might be on the right track. So we have 4, 5, 6, 0, 0, 0. And we have 1, 2, 3. Does M have to equal N? Probably not, or else they wouldn't give it two different variables. Yeah. Okay, so I'm thinking we have to return it in this one. So the less value always has to go here. So if you swap those two, and now what? So would J go up by 1? And then I goes up, yeah, I goes up by 1, and then J. So would you put it like this? And then here, so maybe J goes up by 1 if you swap it, I guess. Is that just it? I mean, this is impossible. Those test cases don't help me at all. So J, so now J is out of bounds. So either I or J is out of bounds. So this is out of bounds, huh? Well, J, I guess we don't want it. Can I add this as a test case somehow? I guess I'll just keep submitting it. So maybe we don't need to increment J anymore because we did it up there. No. That looks good. So let me print what I equals and then maybe what J equals as well. My submissions are going through, right? All right. There. So J is a 1 and I is 3. Maybe we have to say while I is less than M and J is less than N. And then whichever one finishes first. Well, do we reset J? Because if J finishes first, all the numbers are still in J. Okay, now we have a new test case. So 4 0 0 0 0. All right, let's look at this one. So we have 4, and then 1 2 3 4 5 zeros. 1 2 3 4 5. 1 2 3 4. Yep. And then nums of 2 is 1 2 3 5 6. Okay, so we have I and J. J is less than this one, so we're going to swap it. Like so, and when we swap it, J and I both go up. Is that incorrect? Should I stay the same? No, because that was the smallest element, so I should go up. And now I is... This is not true anymore because I equals M. So I and J will both be here. And then we want to fill in J. So this looks good. So we don't want to reset J to 0 then. Because now we just want to say... So we don't want to reset J to 0, but that worked with the other one. So now it's out of bounds. Okay, so let's look at this example. Um, 1 2 3 and 2 5 6. Okay, so I is here, J is here. I goes up because it's less than. That's a 2, right? Yep, so I goes up. Now these swap. And now they both go up. Yeah. But we should really have J be here. So it looks like J didn't want to go up there, so why not? So we had it like this. I and J are here. But I'm pretty sure if I take away this, then it doesn't make any sense at all. Because that other example we had, J did have to go up. So maybe if one goes out of bounds, then we don't move the other one up. So we could say like if j is greater than or equal to n, then just break there and don't move up I. These test cases don't matter. J is still 1. So it breaks down here. But J is still 1. Why is J 1? Oh, should we check? I've coded too much today. Okay. Alright, yeah, I'm just gonna finish this one. I've coded for, well, it's been an hour recording. And I did this 2-hour thing earlier. Yeah, it's been a lot of coding recently. So this is good. I feel like the mental state I'm in right now kind of matches where I'm at towards like the end of take-home assessments, where I just am kind of reluctantly banging my head into a problem that I feel like I can do, but for some reason I'm just not able to step back and articulate exactly what's going on. So I find when I'm in this state, I should just zoom out. I should zoom out. So we always want our pointers to be on the minimum numbers. So let's look at this case. So our pointers start at 0 because they're both sorted, so we're on the minimum numbers. So we need to know which of these is smaller. It should go in the very first place of our result list. Now, we know that this must be the smallest number because it was this smallest or this smallest. So now, like we could have, so whatever's here has to be bigger than or equal to 4. And whatever's here has to be bigger than or equal to 1. So what are the next smallest numbers? So I believe we actually want, so I needs to go up because it's the next answer. J, does J need to increase? Well, we know that this is greater than or equal to 4. So if this was 5, for instance, then we'd want to move 4 back. So at this point, though, I has went out of bounds. I has went out of bounds. So when I goes out of bounds, then we want to add, now this is kind of hard. So when I goes out of bounds, we want to add 2, 3, 4, 5, 6. Is that the problem that we're having? So when I goes out of bounds, we want to add this, but this is no longer sorted. So this is tricky because we can say like, yeah, let's move 2 or let's move J, but how are we going to know the order of this? So I don't know. That seems like a tricky one. So let's go back to the basics. We have 1, 2, 3, 0, 0, 0, and 4, 5, 6. So this problem is pretty one-sided, and I feel like it's not a great example. Okay, because it's actually 2, 5, 6. Okay, so that's a little better. So 2, 5, 6. Okay, so we're going to set our pointers I and J. We want the smallest between those to be in this position. So we identify it as I, so we just move I up. Okay, so now here we have a tie. So in the case of a tie, I think we want to move I up because the way I'm thinking about I is like, this is where our next answer needs to go. So we don't need to, like, switching won't really help us because 2 is already the next smallest and it's in where it has to go. So then we can move up I to 3. And now this is interesting because now J is like, nums 2 of J is the next smallest. So we should swap them because this is where it should be in the order. Okay, so there's like 2 sort of cases I'm noticing. So here we did have 2, 5, 6. But what if, yeah, so this is what was happening in the other problem. What if this was a 7? And instead of 3, 5, 6, we had 7, 5, 6. If we had 7, 5, 6, this is a problem because now this list is no longer sorted. So if this was a 7, what are we supposed to do? So let me consider a new test case, which is 1, 2, 7, 3, 5, 6. So I and J, 1 is smaller than 3, 2 is smaller than 3, 3 is smaller than 7. So I would swap these, but now this is no longer sorted. So I don't know what I would do here. Could we instead, well, I don't know. I was going to say, could we move it to a 0 position? But I don't know if that helps us because what if it was like in between these two numbers? We can't accurately determine which 0 it goes into. Maybe we can just put it into a 0. So why would we do that? Why would we do that? What if it was a 4? Would we still do this? So what I'm saying is if J is ever bigger than, oh, well, it can't be 7. Wait, no, it can. Yeah, it can't be 7. So if it's 4, so if this was 4, if it's 4 and 3, can we do that where we just like put it in the zeros? So can we say, okay, here J is less than, so can we put it where I is, and then this can go to I plus 1? Maybe that's the trick, because now this guarantees that both the lists are sorted. Whether this is a 7 or it's infinity or whatever, and then J would go up by 1. And this would just be null or something. it's still sorted. So then we would go to the next spot, and then we see that 5 is bigger, so then we just move to the 0. And then we see we're out of bounds. It equals a 0. Does it matter? Can it be negative? Can the numbers be negative? So no. Yes, actually. So we can't really look at this as a 0. So how do we know it's out of bounds? So right now I is 0, 1, 2, 3, 4, and j is 1. Combined, they have 6. So is it when I plus j is greater than or equal to m plus n? Is that when we stop? So that's a new idea. So when we encounter something that's bigger, so let's look at the other idea. So 4, 0, 0, 0, 0, 0. And I think it was just 1, 2, 3, 5, 6. So we'll have I and j. 0 plus 0 is not bigger than 6. Okay, so j is smaller. So we're going to move, but instead of putting 4 here, we're going to put 4 here where this 0 is. So we're going to put it at I plus 1. And of course, j will go up. So now it's 1 plus 0 is not greater than or equal to 6. I goes up as well. So I'm just going to comment that. So right now I'm saying if j, not the index, but the item. So it would be if nums2 of j is bigger than nums2 of I, then we say, well, if it's bigger than, we don't do anything. If it's less than, so that means we need to do something, then we would say nums1 of I equals nums2 of j. And, well, I guess we would say nums1 of I plus 1 equals nums of I. So we'd say this. And then we would say, well, j must go up by 1, and I must go up by 1 as well. That's my new thought process. Okay, and now we'll look at 4 and 2. So 2 is bigger, so it has to go in this point. So I will go to I plus 1. We overwrite whatever it was, we don't care. And then 2 goes where I is, and then we increment both of them like this. So now they're still both sorted. All right, same thing, because 3 is less than 4, so we'll move over here. And then move this there, and then move both of them over. And now we have 0, 1, 2, 3, so I is 3, and this is 0, 1, 2, 3. Right, because it was red will be removed. So it was 1, 2, 3. So 0, 1, 2, 3. 0, 1, 2, 3. So, but we don't want to stop, so I think maybe we can get rid of this. Say if it's greater than it, then we stop. Okay. So now I is actually like 4 should go here. It's the next smallest thing. So in that case, I goes up. And now this is no longer true because it's 5 plus 3 is greater. This is true because 4 plus 3 equals 7, which is greater than m plus n, which is 6. So in this case, because I is I is the one that went out of bounds. So J is still less than M. So in that case, we basically just fill in the rest. Okay, so this works for that. Now, what's an example where J is going to move every time? So J goes up whenever J has the smallest numbers. So what if we have an example 4, 5, 6, 0, 0, 0, and 1, 2, 3? This example should make J go all the way to the out of bounds. So we'll start I here and J here. So J is smaller. So this, oh, does it all fall apart? Because I move 4 here, delete 5, and then J goes over here. So 5 has been deleted, unfortunately. Five has been deleted, folks. 5 has been deleted. Yeah. So before, what I was doing is doing this, like that. I'm getting a phone call, 1 second. All right, I'm back. Yeah, so I think I'm just gonna do it like the normal way and just think about how I would do this one. So I'll just have a third array. Ah. Yeah, because I know how to do this. I know how to do this problem. I just don't know how to do it in place like this. Because we could move like everything over and then add 4 here, but to move everything over is linear. So I really don't know. So I'm just gonna write I guess I could just write like the basic sort of script for it. Where you say while I is less than M and J is less than N, if, then we'll just have like a result. If nums1 of I is less than nums, I guess, or equal to nums2 of J, then we'll say result dot append nums1 of I and I plus equals 1. Otherwise, result dot append nums2 of J, J plus equals 1. Then we'll say if J equals N, then while I is less than M, result dot append nums1 of I plus equals 1. Otherwise, while J is less than N, result dot append nums2 of J, J plus equals 1, nums1 equals res. Okay, so this is basically just the standard way of doing it. So let me see if I got any errors there. So let me print result here, I here, and j here. I wish it showed me the real test cases. I don't know how to... I accidentally clicked X, and I don't know how to undo it. Oh, use test case. Okay, that's so much better. All right. So we have 1, 2, 2, 3. And then I is 0, 1, 2, 3, and j is 1. That makes perfect sense. So because j is out of bounds, well, okay, so I is 3, which means j is in range. So this else block would execute. What is the result? So it seems that this is not working. So shouldn't this be executed? So it seems that's not being executed. 1, 2, 2, 3, 5, 6. Should I be doing n plus 1? Two, 2, 3, 5. Oh, so does this part not work? Yeah. Okay, well, at least I did it this way. So yeah, I don't know how to do it in place. So today I solved these 3, and I was unable to do merge sorted array in place. So I could do it if you use another array, but I don't know. Could I say 1 equals... I don't think this will work. This might work. Yeah, but it's still not really. Yeah, that doesn't count. Yeah, so I'm not sure how to do it. I tried some swapping stuff, but yeah, I think I coded a lot today. Yeah, I coded a lot today, so I'm just gonna take it easy for the rest of the day, and then tomorrow I'll be back with the LeetCode roadmap. So tomorrow I'll probably do I might try 2D dynamic programming, or maybe advanced graphs, or maybe tries. I don't know what this is. Maybe I could do some stack problems actually. That might be good because I feel like it's hard to do daily coding and learn new things, because all of these topics I've done so far are kind of, with the exception of heaps, I already knew them, so it was more like reviewing, and I didn't really know backtracking. But this stuff I don't really know, so I'll kind of have to learn it as I go. But I think I should just remember that the goal isn't really to solve the problem, and learning is the goal. So it's okay for me to just spend 30 minutes to an hour on a problem and not get it. But then just like look up the solution after. So, all right. Anyway, super long episode today. So I did, to recap, remove duplicates from linked list, sorted linked list, find the square root of a number using binary search, longest common prefix of several words in an array, and then I failed on merge sorted array. So thank you guys for watching. So it was day 52, and I'll see you guys tomorrow for day 53.